So today we're talking about special line segments and their points of concurrency of a triangle. So the first special line segment that we're going to talk about is the angle bisector. And guys, it does just what it says. It's going to bisect an angle. When we bisect an angle, we cut it into two congruent angles. Now, his point of concurrency is called the incenter. So here's what we're actually talking about. We're talking about the center of an inscribed circle. So inscribed simply means it's on the inside of the triangle. So that's what I've written over here. And this is the takeaway from an incenter. It is equal distance from the sides. Okay, so it bisects the angle. So notice I highlighted that guy because if it's an incenter, it's going to bisect each vertex, but it will be equal distance from the side of the triangle. So from Q to F, from Q to D, from Q to E are all the same distance, because think about it, guys, that would be the radius of the circle. So if you have not printed these notes, I would print them and then highlight and make your notes as you go. Perpendicular bisector, we've talked about this guy, but we've talked about him more in just one triangle than we have with a point of concurrency. So we know perpendicular means it's going to be from the vertex to the opposite side, forming a 90-degree angle, and it's going to bisect or cut the side of the triangle into two congruent pieces. So a segment that is perpendicular to the side of a triangle and goes through the midpoint, because again, remember, if it's a bisector, both of these are congruent, which would make this guy your midpoint. Okay, same here. It might not be the absolute from the vertex, but if it's perpendicular to the side, just remember it's going to go through the midpoint. Now, his point of concurrency is called the circumcenter. So here he is right here. Now notice on this one, guys, the center of a circumscribed circle. So the circle is now on the outside of the triangle. Do you see the difference in these two? This guy is on the outside of the circle, and he is equal distance from the vertices. So I have highlighted the special line segment. He is a perpendicular bisector. He's perpendicular to each side of the triangle, forming a 90-degree angle going through the midpoint, which means both of those segments are congruent, but he is equal distance from the vertices. So notice on this one and on this one, when we talk about the distance, they are in dotted lines, but your actual special line segment is highlighted. Next, we have a median. A median. It's a segment from the vertex to the midpoint of the opposite side. So a median goes from the vertex to the opposite side's midpoint. So again, you're going to have two congruent pieces, but guys, don't confuse him with a perpendicular bisector. Perpendicular bisector forms a 90-degree angle, where a median is just a segment. His point of concurrency is the centroid. We're going to do a little bit more work with him tomorrow, but a centroid is 1/3 the distance from the midpoint to the center and 2/3 from the center to the vertex. So here, 1/3 from the midpoint to the center, 2/3 from the center to the vertex. And then altitude. This is probably the most common special line segment. He's a segment from the vertex that is perpendicular to the opposite side. Notice that we do not have any marks about the segment. He is just a line that forms a 90-degree angle. His point of concurrency is called the orthocenter, and here he is right here. There's not a lot that's special about the altitude other than the fact that he forms a 90-degree angle. And that's it. He doesn't do anything else. So in the back of this sheet, we have some practice with your special line segments. So here, an angle bisector, he bisects an angle into two congruent angles. We found our picture down here that relates to an angle bisector. his point of concurrency is an incenter, and his special properties are he is equal to the sides. Okay? Perpendicular bisector is perpendicular through the side of a triangle at its midpoint. His point of concurrency is the circumcenter, and he is equal to the vertex. Median, vertex to the midpoint of the opposite side. His point of concurrency is a centroid, and that centroid, he is 1/3 the distance from the midpoint and 2/3 the distance from the vertex. And then the altitude, like we said, from the vertex perpendicular to the opposite side, going through the orthocenter, forms a right angle to the side. That's it. He doesn't have any other defining properties. So what we've done here is identify the special line segments A through H, and then their special properties on the bottom as well.